Hey Algebra 2, here is your lesson 9.4 talking about common logarithms. So we're going to start by matching each expression from the first column with an expression from the second that has the same value. However, if we want to be able to match them, we need to know what their values are. So let's just go ahead and start doing that. We know that anything where the base matches the parentheses automatically becomes 1. That's an easy one. The next one's a little bit harder. Because it doesn't have a base and it's not set equal to anything, we have too many variables to work with. So for this one, I'm going to go ahead and throw it in the calculator and see what that tells me. It's approximately 1.079. So let's use that, 1.079. 2 actually, I'm going to give it a fourth decimal there. And hopefully we'll get another one in the second column that's really close to that value. For the next one, it doesn't work for me in logarithmic form, so I'm going to throw it into exponential. I'm going to write 3 to the x equals 1. I know that the only way to get 1 as an answer would be for x to equal 0. So the answer for this one is 0. The next one is another one where I'll have to change it into my exponential form. I get 5 to the x equals 1 over 5. The only way for something to go from the denominator up to the numerator is to make it a negative exponent, so that right side becomes 5 to the negative 1. And 5 to the x equals 5 to the negative 1 means the x is just negative 1. The last one here is another tricky one. Because it doesn't have a base and it's not set equal to anything, I'm just going to come back and put it in my calculator to see what that tells me. That one's nice. It turns out to be just 3. All right, let's do the same thing with this side. I get 4 raised to the x equals 1, because when I change it to exponential form, technically it's equal to an unknown. I know the only way to get to 1 is for x to be 0. Log base 2 of 8, rewrite it as 2 to the x equals 8. 2 times 2 is 4, 4 times 2 is 8, so x ends up being 3. Log base 10 of 12. This one's a little tricky. When I throw it into exponential form, it doesn't really help me that much. So I'm just going to leave that one alone for a minute. Next one's not so bad though, because when I put it into exponential form, I get 5 to the x equals 5. This is similar to the first one we did in the first column, because anything with the base the same as its parentheses is going to be 1. Putting it into exponential form just proves that. And then the last one is another one where if there's no base and it's not set equal to anything, the only thing I can really do is put it in a calculator. I get negative 1 there. So let's start matching things up here. I have a 1 and a 1, so this is IB. I have a 1.0792. I don't have any of those over here. I'm going to assume that it's number 3, because you've got log of 12 and you've got a log of 12, and those probably match up somehow, but I'm going to leave it alone for just a minute. This one is 0, so I can for sure match it up to the first one there. This one's negative 1, I can match it up to V. And then this one is 3, so I can match it up to 2. And because 3 is the only one left here, it must be that. So when I look, if I put this in my calculator as log base 10, and I can do it in my calculator because I have a change of base log in here somewhere. Maybe I'll be able to find it to show you. Oh, there it is, log base. Yep, so I can put my base in here, and I can put this in the parentheses, and I do find out that that does give me the same value of 1.0792. So let's take that off to the side and just look at it for a minute. This tells me that log of 12 is equal to log base 10 of 12. And what we're going to start talking about today is that when something doesn't have a base, when it doesn't have a number right behind the log, we're going to be able to assume that that number is actually a 10. So let's go down here. read for a little bit. So logarithms of base 10 are called common logarithms because they have many applications. So they're the most common type of logarithm we're going to work with. So two really big things you need to be aware of are that the Richter scale as well as the pH scale use common logarithms. So let's look at how they're used. The amount of energy E in ergs that an earthquake releases is related to its Richter scale magnitude M by the equation given there. So the Chilean earthquake of 1960 measured an 8.5 on the Richter scale. We need to find out how much energy was released. So when I do these problems, I either like to highlight in the problem my important information, or I like to bring down my knowns. And for those of you who took the ACT, this is a skill that maybe you've seen before. But if it hasn't, this can be really helpful for word problems if they scare you a little bit. So log of E is equal to 11.8 plus 1.5 m. It said that the Chilean earthquake had a magnitude of 8.5, so I say magnitude of 8.5. Now that I have all my knowns written down, I can just plug stuff in. I'm solving for E, and I have my M. So log of E is equal to 11.8 plus 1.5 times 8.5. I can throw that in a calculator really quick and find out that it's going to be about 24.55 equal to log of E. Because I know that this is a common log, I know that the base is equal to 10, so I can right away go ahead and change this into exponential form and say that 10 raised to the 24.55 is equal to E. And then when I throw this in a calculator to simplify it, I find that E, or the ergs of this earthquake, were 3.548 times 10 to the 24th ergs, and I do want to label it appropriately. So, common logs, very useful. Not only are they very useful, but I think they're kind of easy to work with because most of the time we can just plug them into our calculator. So my calculator does something fancy where I can do any log base in it, but I have to find the special button to do that. If I just use the basic log button on my calculator or on one of your scientific calculators, it's automatically going to assume that you are using a common log with a base of 10, which is really nice because we can just plug these in directly and write out what they're equal to. So if I say evaluate this common log, these are going to be the ones you like because you can just throw them in a calculator. Log of 5 is 0.6990 when I round. Notice because I'm rounding that 7 up. So let's keep going for those moments when we can't necessarily plug it into a calculator. If I tell you that log of x is equal to the given number in 3 and 4 here, we need to find x. But this really shouldn't be that much more difficult than what we've been doing because all we're really taking on here is exponential form. We're saying if we have no base, we know that it's automatically a 10, and then we just transfer it over to exponential form like we've been doing in the previous unit. Once I've got it in exponential form, I can plug it into my calculator. I put those numbers in backwards. Give me 1 minute to correct that. There we go. 145.2112. And yes, I do want you to calculate these out. I don't want you to leave them in this exponential form. I want you to be able to actually put them into the calculator and give me a full number. All right, let's do the same thing here. I use a common log. Say log of x is equal to negative 1.42. I know that my base is 10, and I raise it to the negative 1.42 power. I'm going to put that into my calculator. And when I do, I get 0.0380. 0.0380. So even when they're not as straightforward as examples 1 and 2, they're not bad as long as you can go back and forth from exponential to logarithmic. That is still a really important skill. So if you're still having problems with that, come work with me so that we can make sure you're really strong on that before the test. So we've already talked about the next thing coming up. It was called the power to power rule, and it allows a power to become a multiplier when we're using a logarithm. So if you remember what this looked like, it was something that looked like log base b of m raised to the power ended up being equal to, or we could turn it into, the power being a multiplier out in front of our logarithm. And we're going to use that idea a little bit more to solve problems that we previously couldn't or that would have taken us a really long time. So if you were confused by this rule before, we're really going to hammer it home now. So let's flip to the back side. So this first one asked me to solve for x. And what I'm going to do is, you would think we're just going to go right into log form. We're going to go from exponential to logarithmic. But what I can actually do is take the logarithm of both sides. Remember that algebra property that says if you do it to one side, you have to do it to the other, and that's really all you have to do to keep it balanced. So if I say log of 4 to the x, and I say log of 21, I've technically kept everything balanced because I took the log of both sides. Now all I need to do to solve this problem is to use that power to power rule that was on the previous page. This exponent that is inside the parentheses, I'm going to bring it out and put it in front of my logarithm so that it's x times log of 4 equal to log of 21. Now, why did I do that? Why do I care? Well, if I'm solving for x, all I have to do to get this log 4 away from x is divide both sides by log of 4. And I can do this, and I can divide them because they're common logs. They have a base of 10. We assume that because they have a base of 10, we can divide them. So I'm going to say log of 21 divided by log of 4. And a quick thing in my calculator, notice that when I put this in, I completed my parenthesis after my 21. If I had not done that, it would have told the calculator to take the log of 21 divided by the log of 4. We need it to be two distinct ideas in the calculator, so make sure you're careful with those parentheses. When I hit enter or equal, I get my answer where x equals 2.1962 here. And just as a general rule, when we're working with logarithms and exponents, I tend to prefer about 4 decimals. That allows you to be accurate, but not have to write everything else. And if you're thinking about earthquakes, we do want to be accurate, probably out to that 4th decimal. It does make quite a difference. All right, let's keep going. We're going to do the same thing to this one. As long as I'm taking the log of both sides, I have kept the equation balanced. But again, I don't like working with exponents inside of my log, so I'm going to bring that out front and say 2x plus 1 times the log of 3 equals log of 12. Why do I like this? Well, because technically log 3 is just a number. So all I'm doing when I divide both sides by log of 3 is dividing a number by a number. And I end up getting 2x plus 1 is equal to log of 12 divided by log of 3. Again, notice I'm being careful with those parentheses. 2.2619. 2.2619. I could go out further, but I'm not going to. Subtract the 1 over, that's just a algebra rule. I get about 1.2619. I guess I could do this in my calculator too. And then, of course, divide by 2. You're going to get an approximate answer of 0.6309. If you're off by 1 decimal place or by a rounding, I'm going to assume it's a calculator error. But again, by going out to 4 decimals, it allows me to see how accurate you really were in your calculations. So please go out to 4 decimals. All right, at this point, I would really like it if you would pause the video and try these next 2 examples on your own. Once you have at least attempted them by yourself, you can go ahead and come back and see what those look like worked out. All right, hopefully you paused the video and gave those a chance on your own. We are now going to do them the same way we did the other 2. So take the log of both sides. Because we're working in base 10, they solve the same way every time. Log of 4 equals log of 12. Divide both sides by log of 4. Log 12 divided by log of 4. 1.7925. Divide by 3. You get x equals 0.5975. You can tell I'm really bad with my approximate equal sign, but I won't mark you off if you put an equal sign because I understand that it's rounded. All right, let's do another one here. This one's got a lot going on both sides, but we treat it the exact same way. Log of 9 raised to the 3x equals log of 4 raised to the 5x plus 2. Those both become the multipliers out front. I like to put my logs in parentheses just to remind myself that I'm really just working with a number. Just like that. Now all I have to do is get rid of those logs. However I want to do that, I could divide by the log of 9. I could divide by the log of 4. In this case, I think I'm going to divide by log of 4. I just like working with the bigger number on top, I guess. So 3x outside of whatever number that ends up being. Log of 9 divided by log of 4. 1.5850. 1.5850 equals 5x plus 2. Yeah, let me just check to make sure I did that right. Yep, so I'm going to multiply that in now to get this side to be approximately 4.7549x equals 5x plus 2. Solve for x. I get negative 0.2451. X equals 2. And x ends up being, let me just double check my notes here, approximately negative 8.1599. All right, so there is that. This unit is really going to test those basic algebra skills. Can you solve for x? The setup itself is not that challenging as long as we remember our power to power rule and taking the log of both sides. After that, it does get a little hairy down in here because you have to remember how to solve for x. All right, last one, and it's a word problem. These are my favorite. So there are initially 1,000 bacteria in a culture. The number of bacteria doubles each hour. The number of bacteria n present after t hours is n equals 1,000 times 2 raised to the t. How long to the nearest minute will it take the culture to increase to 50,000 bacteria? So I'm going to start out with my knowns just like I did before. Knowns. Initially, there are 1,000 bacteria. I'm just going to say BAC. The number of bacteria doubles. The number present after t hours is that formula. N equals 1,000 times 2 raised to the t. How long to the nearest minute will it take the culture to increase to 50,000? So I want to know time equals question mark. So if I know that I want my number of bacteria to be 50,000, I'm immediately going to plug that in for my n. So 50,000 equals the 1,000 times 2 to the t. And now all I'm doing is quickly solving for t. So go ahead and divide that over. You get 50 equals 2 raised to the t. We can't really do anything with it in logarithmic form because there's nothing that 2 multiplies 2 or can be raised to get 50. So I'm going to take the log of both sides and say log of 50 is equal to log of 2 to the t. I'm going to flip these over just because I like working with my variable on the left side. And in the process, I'm going to use my power rule that says I can bring the power out to be a multiplier. Equals log of 50. Again, I'm just solving for t by dividing both sides by log of 2. And I end up getting that t is equal to about 5.6438 something, ... I could round. But then I, of course, have to take that into consideration of it being minutes because t is currently in hours. So if I want to find out in minutes, I just have to multiply that by 60. So convert to minutes, I get that t is equal to 339 minutes. And I'll just write times 60 here because we had to go from minutes to hours and hours to minutes. All right, that's all there is to it. Go ahead and give that homework a try. If you have any questions, don't hesitate to reach out.